Hello everyone. Thank you for joining the 2024 IEEE LEO SatS and Space Environment Workshop. And thank you for inviting me to be part of it. Today I'm going to introduce the topic Space Robotics-based ISAM to support space debris mitigation. My name is Flores-Abad. I am an assistant professor at the Aerospace and Mechanical Engineering Department of the University of Texas at El Paso. And I am an affiliated researcher at the university's Aerospace Center. The contents of today's presentation is as follows. First, I'm going to give a brief introduction to the important topic of space debris. Then I will explain how space robots can help in mitigating this problem by using them in ISAM-related activities. ISAM stands for In-Space Servicing, Assembly and Manufacturing. The first component of the presentation is associated with on-orbit servicing. Subsequently, I will present a few projects that we have developed in this field by our group. One is about the use of space robots and augmented reality to perform servicing operations. The second is in regards on-orbit manufacturing and assembly as a tool to support space debris reduction. Then I will show a robotics-based project to perform additive manufacturing in a space-like environment, considering vacuum conditions. And finally, I will give a brief introduction to our small satellite effort, which includes the development of a small robot as payload. As of 2021, there were 34,000 objects larger than 10 centimeters in orbit, from which only 20,000 are properly identified and cataloged. Besides, there are around 2,000 active satellites, from which less than three-quarters are maneuverable. The rest are orbital debris, large parts of launcher upper stages, mission-related objects, and inner pieces from fragmentation or collisions. Besides, the mass of space debris in space is over 3 million kilograms, and there is no signs of slowing down. This problem might produce collisions at hypervelocities. Therefore, there is a need for objects to be identified, captured, towed to a different orbit, to be reactivated or repaired if possible. Here, I introduce two examples of satellites that burns throughout all its fuel. After 9 years in deep space collecting data, that indicated that our sky is filled with billions of hidden planets, more planets even than stars. NASA's Kepler Space Telescope ran out of fuel. The fuel was needed to continue further mission operations. Therefore, NASA decided to retire the spacecraft within its current safe orbit, away from Earth. In this case, it would have been very useful to be able to refuel the spacecraft and prolong its life. But with the current technology, was not possible. Besides, After 11 years of operation in space, in 2018, NASA decided to retire the Dawn spacecraft for a similar reason. Presumably, the thrusters ran out of fuel, which prevent the spacecraft from establishing contact with Earth, as the antennas couldn't be oriented towards the Earth, and the power generating solar panels couldn't be oriented towards the sun. These are two examples that shows the need of on-orbit servicing, on-orbit repair, on-orbit refueling. In order to reduce the amount of space debris, some of the malfunctioning or retired spacecraft should be captured to repair them or refuel them. For this purpose, different techniques have been proposed. For instance, the use of mechanisms with tentacles inspired in octopus and spiders. But one of the most promising technologies includes the use of robotic arms to capture the pieces of space debris. That means a robotic arm mounted on a base satellite. In this regard, different missions have been proposed to achieve the goal of capturing a malfunctioning object in orbit, such as the Orbital Express mission and the DOS mission. This slide shows some of the phases and tasks that have to be performed by a space robot to capture a malfunctioning satellite in orbit. The satellite might be out of control and tumbling, difficulty in the capturing process, and making it dangerous as well. The video shows that the first phase is the observation and planning phase. During the observation and planning phase, some of the objectives are to estimate the mass properties or parameters of the target satellite. Another may include the 3D mapping of the same object, or even inspection. The second phase is a final approaching phase where some areas of interest include soft capturing, the minimization of the disturbances on the base spacecraft due to the robotic arm motion, some safety considerations, of course, robotic path planning and collision avoidance. The third phase is the interception and capturing, which has the objective of reducing the momentum of both of the systems to the tumbling. In this case, there is interest to develop time and energy optimal algorithms, for instance, or methods to have a coordinate motion between the robot and the spacecraft. Once the robot has been able to capture the target satellite, then we can proceed with the repair, refuel, or upgrade of the space asset. Here, I'm going to introduce a augmented reality-based robotic system to support in-space servicing. Augmented reality can provide the human operator with a 3D dynamical view of the target spacecraft to select the best perspective and view of the region of interest so that the repair path can be planned appropriately despite the presence of occluded zones. Occlusion in space may occur due to the presence of an object on the top of a region of interest that prevents the robot from having a good view of the area to repair. Another source can be the amount of light. The robot can be operating in shadow or can be operated in direction light, difficulting the path planning of the repair task. Therefore, having a 3D dynamical view of the target based on an augmented reality system can help to perform the operation despite the occlusion. In this case, the teleoperator will be able to manipulate the 3D model in first person to guide the robot and avoid undesired collisions or excessive force exertion. In this project, there is a local environment where the operator lives, which is a real environment, and the operator has a head mounting device that allows him to visualize the model of the system. There is a virtual environment or 3D virtual representation of the real space asset and a simulated remote environment or target satellite in orbit. In a realistic case, the simulated remote environment will be the actual real environment in orbit. This slide shows with more detail the simulated remote environment, which includes the servicing robot that features a base spacecraft and a 6 degrees of freedom robotic arm, which will perform a repair task of a solar panel. A solar panel might be damaged during launch due to the high vibration loads or due to electric discharges in orbit, for instance. So, in this example, the robot should deposit a conductive ink per se to repair probably a open circuit or so. In the augmented local environment, we have the human operator and we have the spacecraft simulated system. The human operator will use the model, the virtual model, to recreate the trajectory that the robot should follow for the repair task. As we can see in the figure, in this scenario, the trajectory to repair should be in both sizes of both sides of the solar panel. And it will be difficult for the robot to perform the trajectory in the occluded back plane without the guidance of the human or without the human indicating the trajectory to repair. As we can see here in this figure, the robot has to perform the repair task in an area that is not only difficult to reach but difficult to see. I'm gonna play the video that explains how this maneuver is performed. In space manufacturing and assembly has also potential to reduce space debris. For example, we can manufacture tools and components in orbit to repair and replace parts. Then we can also use space robots to install, assembly, or replace those broken components. And it will also increase the flexibility in the repair tasks. However, it is difficult to perform these activities in outer space due to the harsh space environment, subject to vacuum, reduced gravity, and radiation, for example. The figure shows the concept of using multiple robots to manufacture large components in orbit. A project related to in-space manufacturing and assembly we are working on is related to space welding. However, before performing the welding process, we first need to perform the joint fit up of two components, in this case, two triangular parts as example. So we have a system with a robotic 6 degrees of freedom robotic arm and a 2 degrees of freedom free flyer small robot. They both have to coordinate to perform the joint fit up of these two components. The system includes a set of cameras to monitor the process and make sure that we achieve the required precision and process control. In this case, we have to make sure that the gap picking as mismatch of the two components are according to the requirements. Here, I'm going to show a video that illustrates how the two robots move to perform the joint feed off of these two triangular parts, and we will be able to see also the response of the vision system to ensure process control. This is a project on the use of robots to perform additive manufacturing in a space-like environment. The focus of this one is to perform 3D printing in vacuum and to analyze the process. Uh, as we can see in the figure, we have performed the 3D printing of different geometries, including a star, and we can see the star 3D printed in regular atmosphere and the star 3D printed in vacuum. Of course, the one printed in vacuum has some defects due to the lack of convection and due to the outgassing. This slide shows the video of the robots performing the 3D printing of the two same parts in regular atmosphere in the left and in vacuum in the right. As we can see, the part being printed on the vacuum environment exhibits some defects due to the lack of convection in vacuum and due to the outgassing. That's why we can observe some bubbles on the part. Therefore, new processes, new materials need to be developed to support additive manufacturing in a space environment. Here I show our small satellite effort, named SleeperSat-1, which features a robotic arm as payload, or as one of its payloads. This is a 3 degrees of freedom robotic arm that will perform different maneuvers in orbit where motion, dynamics, and control algorithms will be tested and validated. The motion will be recorded via encoder measurements and also a camera. This is a technology demonstration mission to further advance some algorithms that in the future will be used in other robotic missions to support ISAM activities in space, servicing, assembly, and manufacturing, including, for instance, on-orbit servicing and on-orbit assembly. The satellite includes different components such as communication system using UHF and S-band antennas, and ADCS for attitude determination and controls, an onboard computer, an electric power system, and electric generation system through the solar panels. It is expected that the robot will operate in free flying and free floating mode to validate the algorithms. I want to thank you for the opportunity to participate in this event and give this presentation. If you have questions or comments, please feel free to reach out to me. Here I'm leaving my email address, which is the easiest way to reach out to me. Please feel free to contact me if you would like to learn more about it or you just have questions. Thank you again.